Hi everyone, welcome to Budding Genius Academy. My name is Amelia and I'm currently studying mathematics and statistics at the University of Toronto, and I've been a math tutor for about 4 years now. I love math and I love teaching people new things, so hopefully I can teach you guys something new today. If you like the lesson that you see in this video, you can register for our summer camps or our tutoring service at www.bg-academy.com, and if you get the questions right on the quiz at the end of this video, you can email buddinggenius@buddinggeniuscm.com for 20% off of any of the lessons that you book. So, why don't we hop into it? Today we're going to be talking about Pascal's Triangle, and more specifically patterns within Pascal's Triangle. We're going to walk through a couple of the things that are interesting about Pascal's Triangle, and then we're going to have a very short little questions at the end for you to test your knowledge. So, why don't we hop right into it? First off, what is Pascal's Triangle? Pascal's Triangle was named and popularized by Blaise Pascal in the 16th century. Pascal's Triangle is a triangle formed from a series of numbers, and it's constructed like this. So, you have a little triangle, and the first thing that you do is you put ones along the outside. You put a 1 here, a 1 here, a 1 here, a 1 here, and on and on and on, so forth. Let me fill this up so you guys can see. Next, each number is the sum of the two numbers before it. So for example, the ones that we can see right here, we know is the sum of this one and this one above it. So 1 plus 1 is 2. So there's a 2 right there. And then below this one, 1 plus 2 is 3. And then 2 plus 1 is 3. 3 plus 3 is 6. 3 plus 1 is 4. 3 plus 1 is 4 on this side as well. And so on and so forth. 1 plus 4 is 5. 1 plus 5 is 6. 1 plus 6 is 7. 1 plus 7 is 8. 4 plus 1 is 5, 5 plus 1 is 6, 6 plus 1 is 7, 7 plus 1 is 8, 4 plus 6 is 10, 6 plus 4 is also 10, 10 plus 10 is 20, 5 plus 10 is 15, and on and on and on. So maybe you can pause the video and see if you can fill out those bottom 2 rows all by yourself. But if you can't, I will fill these out so you can see. And there you have it. I've chosen to do just these many rows so that you guys can see what the triangle would potentially look like, but you can go on and on and on for infinity, right? Because you could always do 1 plus 8 is 9, 1 plus 9 is 10, on and on for as long as you could possibly imagine. But no matter what you do, it's always going to create this really nice triangle shape, which is why it's called Pascal's Triangle. So, the phenomenon of Pascal's Triangle is the interesting thing about Pascal's Triangle is the number of patterns that you can find within these numbers that you've now created and written down. So let's walk through a couple of these really funky patterns that we find in Pascal's Triangle. The first one that you may have already noticed is that Pascal's Triangle is symmetrical about the vertical line. So what that means is, if I drew a little line right down the middle, the numbers on this side of the triangle are the same as the numbers on this side of the triangle. So you see there's a 1 here, and there's a 1 here, and then there's a 1 here and a 1 here, and then a 1 and a 3, and a 1 and a 3. They're sort of flipped, but they are symmetrical around the middle. And if you want, we can go up to this triangle here that we already did, the bigger one, and if I draw another line right down the middle, you can see for yourself that all of the numbers are symmetrical around that middle line. And that's going to be true for all of them because, as we've seen in the past, 1 plus 3, if you were to do it right here, 1 plus 3 equals 4, but also 3 plus 1 equals 4. So there's going to be a 4 on both sides of the triangle. So that's going to be true of every number on Pascal's Triangle, and thus the triangle is symmetrical. And this symmetry is really what helps distinguish a lot of the patterns in Pascal's Triangle. Alright, here's another pattern that we can start to see, is that along the diagonals, the numbers become significant. Along the first diagonal, I'm sure everybody can see that it's just a bunch of ones, right? 1, 1, 1, 1, 1, 1, 1, 1, 1. And that's because that's how we create Pascal's triangle. We write all those ones along the diagonal. And that is sort of a pattern in itself, I guess, but it's sort of a basic pattern. It's not very interesting because it's just the way that we create Pascal's triangle. But let's take the next diagonal. You can see that because we're just adding 1 to every number going on and on and on, it just becomes the integer numbers. So it just becomes 1, 2, 3, 4, on and on and on. So we call those the counting numbers. And I'm sure you guys have heard of these before. Some people call them integers. They're just the whole numbers that go from 1 to infinity. And that is the numbers that you will always see on the second diagonal of Pascal's triangle. But this pattern extends even further. So we can go into the third diagonal. And this becomes the triangular numbers. So you guys may not have heard of triangular numbers, and that's fine. Triangular numbers are a little interesting. So the way that you create triangular numbers is the first one is just 1, right? So 1. And then the second one is 3, which can be written as 1 plus 2. And then the next one is 6, which can be written as 1 plus 2 plus 3. And then the next one is 10, which is 1 plus 2 plus 3 plus 4. And you can start to see that pattern as well, right? It's just adding the next biggest integer to whatever sum you've already created. And the reason they're called triangular numbers is because you can represent them with dots, and they start to look like a little triangle. So 1 is just 1 dot, and maybe that doesn't really look like a triangle, but this one does here. You got 1 dot, and then you got 2 dots in the next row. And the next one is 1 dot, and then 2 dots, and then 3 dots. And then the next one is 1 dot, and then 2 dots, and then 3 dots, and then 4 dots. And you can start to see how that goes on and on and on, because you're just adding 1 more than the number you've already added to make a little triangle. So that next diagonal is called the triangular numbers. And then the fourth diagonal is called the tetrahedral, and they go on and on and on as well. You can create any sort of pattern with the other diagonals, but they start to get a little bit hard to understand because you can't have them in just 2D. They get way too crazy. But you can see the fun patterns that have already emerged just when you look at the original diagonals of Pascal's triangle. Another fun pattern that you can start to see is the sums of the rows of Pascal's triangle. So, if I asked you to count up all of the numbers that you've seen in each row, what would you get? Now, if you guys want, you can pause the video for a second and see if you can see the pattern for yourself. I'm going to give you 5 seconds, and then I'm going to help walk you guys through it. All right? 5, 4, 3, 2, 1. All right. I hope you guys have seen the pattern for yourself, but if not, that's totally fine. So if we go through, 1, there's no other numbers to add here, so 1 just equals 1. The sum of this row right here, this row, is just 1. But the next row becomes 1 plus 1, which is 2. And then the next one is 1 plus 2 plus 1, which is 4. And 1 plus 3 is 4, plus 3 is 7, plus 3 is 8. And then the sum of this one becomes 16. And this next one is 32. And maybe you guys start to recognize those numbers. But if not, we can say that the numbers 1, 2, 4, 8, 16, 32, and so on are equal to the powers of 2. So 1 is just 2 to the 0, because any number to the power of 0 equals 1. 2 is 2 to the 1, or just 2. 4 is 2 squared, or 2 times 2. 8 is 2 cubed, or 2 times 2 times 2. 16 is 2 to the 4. 32 is 2 to the 5. and that pattern holds all the way. So if we say that this row that I've circled right here, this row, is the 0th row of Pascal's triangle, then we can say that the sum of each row is just equal to 2 to the power of the row number. Right? So if this is the 0th row, it equals 2 to the 0 or 1. If the next row is the first row, then it equals 2 to the 1, which is 2. And that goes all the way through to all the others. So if I said, what's the sum of all of the numbers in the 642nd row, you would know that it was just equal to 2 to the 642. Whatever crazily large number that is, that would be the answer to the sum of the row. And it's true for every row in Pascal's triangle, which is again just another really fun, interesting pattern that we start to see in Pascal's triangle. All right, the next one. If I asked you to take each one of these as a number, if you saw all of the numbers in Pascal's triangle, smush them together to make one number, do you start to see a pattern? So what I mean by that is 1 would just be 1 as well. But 1, 1 becomes 11. And 1, 2, 1 becomes 121. And 1, 3, 3, 1, 1,331. So if you saw these as just a number, what do you think you can sense the pattern is, maybe? Again, you can pause the video, but if not, I'm going to explain it in 5 seconds, all right? 5, 4, 3, 2, 1. Well, this one may be a little bit harder to see, but again, just the same as we did with the 2, 2, 2, this is equal to the row number to the power of 11. And you may have noticed a bit of a hint over here, because I did sort of say it, but it is an interesting pattern. So this 1 equals 11 to the 0, because anything to the 0 is just 1. Sorry, let me scroll up so you guys can see. 11 is just equal to 11 to the 1. 121 is equal to 11 squared. 1,331 is equal to 11 cubed. 14,641 is equal to 11 to the 4, and so on. It starts to get a little bit confusing when you have a number like this, because it doesn't have just single numbers in every single one of the squares. It's got tens in them. But if we were to write this out, we could imagine that it's 1 and 5 is 51, and then the 10, we carry the 1 over to the other. So it becomes 0 and 11 in the next square. So we write a 1, carry the 1, and it's 6 and 1. And this is equal to 11 to the 5. So, same as before, each row is just equal to, the row is equal to 11 to the power of the row number. Which is just a really cool, interesting pattern that you see within Pascal's triangle. And you really start to notice that there are so many interesting things going on with Pascal's triangle. So let's take a look at another one. Alright, so you may not know exactly what a binomial expansion is, and that's totally fine. So I have written out a couple of these numbers, and I want you to say what this would be equal to. So as we've known in the past, anything to the power of 0 just equals 1. And for those of you who understand binomial expansions of x and y, you know that x plus y to the 1 is just equal to x plus y, right? So you could say it as 1x plus 1y. And x plus y squared is just equal to 1x squared plus 2xy plus 1y squared. And then the next one after that, x plus y cubed, is equal to 1x squared plus 3x squared times y plus 3x times y squared plus 1 y squared. And now maybe you start to notice a connection between the numbers that I've written in red here and the numbers within the first couple rows of Pascal's triangle that I wrote out beforehand. I think you maybe will start to notice that the coefficients, or the numbers that are being multiplied to these multiples of x and y, start to directly imitate the patterns within Pascal's triangle. And this is actually a really helpful device, because if I told you what x plus y to the 4 is, that might be a little bit hard to understand. And it may be hard if you had to do all the calculations out on your own. So you're doing like x plus y times x plus y times x plus y and so forth. That may start to get really hard. But if you understand the rule that the coefficients are equal to the row numbers on Pascal's triangle, then we can just say that we know instinctively that it is just 1 x squared plus the next number is 4, so the coefficient's 4 x cubed, sorry, this should be a 4, that's my bad, x cubed times y plus, then the next number is 6, so it would be 6 x squared y squared plus 4 xy cubed plus 1 y to the 4. And that pattern will hold for any row of Pascal's triangle. If you're a little confused as to how we're getting these x and y's, and more specifically their powers, basically you start with x to the 4, and for every new number, the power of x is minus 1, and the power of y is plus 1. So you can see this 3 goes to 2, goes to 1, goes to 0, and y starts from 0 to 1 to 2 to 3 to 4. But that pattern within Pascal's triangle is really easy. So one will always be equal to the other, and if you have, for example, x plus y to the power of 10, and you know what that equals, then you would know what that row, the 10th row of Pascal's triangle would be. Or if you had the 10th row of Pascal's triangle, then you could understand what the coefficients of x plus y to the 10 were going to be without ever having to do all of that really long algebra all by yourself. So that is an example of a row of Pascal's triangle actually being really helpful to allow us to skip a couple steps when we were doing math. Alright, let's move on to this one, because this one I think is really interesting. This one is the Fibonacci sequence in Pascal's triangle. So, just for a quick intro to the Fibonacci sequence, if you guys don't know what it is, the Fibonacci sequence is a sequence of numbers that pops up in nature all the time. But the way that you construct Fibonacci sequence is, I wrote out the first couple terms, but it's essentially, you start with a 1 and then another 1, and every number after that is the sum of the two numbers before it. So, for example, here, 1 plus 1 equals 2, so that's the next number. 1 plus 2 is 3, so that's the next number. 2 plus 3 is 5, so that's the next number. 3 plus 5 is 8. 5 plus 8 is 13, so then that would be the next number of Pascal's triangle, and so on and so forth. That's the way that you create Pascal's triangle. That is the way that you create Fibonacci sequence. I'm very sorry, I believe I said Pascal's triangle earlier. That's wrong. But we can also start to see that pattern occurring within Pascal's triangle. So if we originally took diagonals like this and we saw patterns within them, but now if we took a slightly more flat diagonal, so if this was the first row in that diagonal, and then this is the second, and then this is the third, so that was including this and this number, and this included this number. We can continue with this pattern, so this would be the next one, which is this number and this number, and the sum of all of those slants that we take equal the number in the Fibonacci sequence. So that would be the next one. Let's see here. 1, right? That just equals 1. And then the blue one is also just 1. And then those two yellow ones, 1 plus 1 is 2. Then the next row is the red slant, which is 2 plus 1, which is 3. The next one after that is 1 plus 3 plus 1, which is 5. And then we can take another slant. So it comes along this line right here, in line with all the other ones. And you have 3 plus 4 is 7, plus 1 is 8. So you can start to see that this is exactly the Fibonacci sequence. So the Fibonacci sequence, which is another thing that has all sorts of crazy patterns in it, starts to pop up when you sum up all of these rows in Pascal's triangle. And that is just another really crazy example of patterns really showing up wherever you see them in Pascal's triangle. Alright. This is the last one that we're going to do for today. Personally, I think that combinations are the most interesting thing that you can do in Pascal's triangle, and they're also incredibly useful. So, if I told you I had 4 items, and how many ways can I pick 2 of these items? Well, you could do it this way, right? You could say, I got 4 items, so here's 1, here's 1, here's 1, here's 1. And then I'm going to say I could do these 2 maybe, so that's 1. Or these 2, that's 2. Or these 2, that's 3. These 2, 4. These 2, 5. Or these 2, 6. I can't see any other ways that you could pick 2 of these 4 items. But if I said I have 104 items and how many ways can I pick 22 of them, then that starts to be way too many to do it in that way. So there's an actually really interesting way that you can do that using Pascal's triangle. So let's go back to the example of just 4 and 2. Remember how I said before that this row right here was the 0th row? Well, if you still count that to be true, you can say I have 4 total items, so I go down to the 4th row. So 1, 2, 3, 4, and this is the 4th row here. And then I go 2 in from the 4th row. So 1, 2, and there we go. I have 6 possible ways to pick 2 items from a possible 4. And this is true for anything that you want. So let's do another one that might be actually really kind of hard to do, for example. So I have 7 items, and I want a way to pick 3 of them. Well, I can go down to the 7th row, and it's easy to find these rows because they're the ones that have the actual number as the second one. So the 7th row has 7 as its second number. So it's pretty easy to find, but in case you don't believe me, you can go 1, 2, 3, 4, 5, 6, 7 to have it be your 7th row. And I have 3 that I want to pick, so I have to go in 3. So I start with this one right here. This is my 0th item, and I go 1, 2, 3. There's 35 possible ways to pick 3 items from a possible 7. And that's a little bit too hard for us to imagine, so you're maybe just going to have to believe me on that one, but this is true for any combination that you pick. So, with that in mind, we've come to our little quiz. So I have a little Pascal's triangle down at the bottom there for you to help you out. And I have 3 questions, so we can go through them. And you guys will have a chance to pause, think about it, and then we'll take up the answers, okay? So right now, pause it and try to come up with the answers on your own. And then you can come back and we'll go through them together. All right? Ready? Pause. All right. Are you guys all back? Are you guys got your answers that you think? Well, let's start going through them. So the first question, you have 6 different colored socks. How many ways do you have to pick just 2 of them? Well, let's start, right? We go down to the 6th row, which we can see is this one right here because it has the number 6. Or we can count 1, 2, 3, 4, 5, 6. And then we are asked to pick 2 of them, right? So we can go in 2 squares. 1, 2. So the answer to that question is 15. There are 15 different ways to pick 2 socks from a possible 6 different colors. So you could have just 6 socks and you can wear them for 15 days in a row with all sorts of different variations. They may be a little bit dirty by the end of it though. You may have to wash them. Alright, let's clear the triangle so that we can do the next question. So if you got 15, oh, I forgot, I accidentally erased that. If you got 15 on this question, good job, you got it right. Alright, and the next one. You have 8 different fish at the store. How many options of 4 do you have to pick for your aquarium? So you go down to the 8th row right here, right? This is the 8th row, and we can go in 4. So we go 1, 2, 3, 4, and there we have it. Our answer is 70. That's a lot of different ways to get fish for your aquarium. But there are 70 different ways that you can pick 4 fish from a total of 8 possible fish. So, if you got 70 as your answer, sorry, let me clear the triangle. If you got 70 for your answer for this question, congratulations, you got it right. 70 is the right answer. Now this last question is a little bit trickier. If I told you that the second number in the 15th row was 105, and I asked you what the 13th number of the row was, what would you say? So we can look down at this triangle and we can say, oh, there is no 15th row. And it would be a lot of work to find a 15th row because you'd have to add up every single one of these numbers, and it would get bigger and bigger and wider, and you have more and more numbers to add up. But this is really important to remember, that thing that we talked about at the very beginning. I know it's hard to remember, but we went all the way back and we said that Pascal's triangles were similar about the vertical. So, in this row here, which we now know is the 4th row, the first number is the same as the 3rd number. So, the the 0 plus 1 number is the same as the 4 minus 1 number. So if we go all the way back down here, we can look at the triangle again and we can say, for example, the 8th row, the second number, 1, 2, is the same as the 6th number, right? This one right here and this one right here, which is 8 minus 2. So if the 15th row, the second number is 105, then 15 minus 2 is the 13th number, and that 13th number will also be 105 because of the symmetry about that middle axis. So the 13th number in the 15th row of Pascal's triangle is 105. And you don't need to do any addition or any math to figure that out on your own, except for maybe 15 minus 2, if you realize that Pascal's triangle is symmetrical right around that middle line. And there you have it. Those are all 3 questions on our little quiz. So I hope you guys got them all right, and if not, I hope you understand what happened. You could always leave a comment below and ask for clarification if you want. And if you did get all 3 right, you can send an email to this email right here, buddinggenius@buddinggeniuscm.com, for 20% off of your booking for any tutoring or summer classes. And I really hope that you guys enjoyed learning about Pascal's triangle today. And if you did enjoy this lesson, these sort of lessons will run every 2 weeks, so you can subscribe below to the Budding Genius Academy channel, or you can register for our courses and get this sort of information all the time. I hope you guys really enjoyed learning today. I really enjoyed teaching you guys something new, and I hope you guys have a wonderful day. Bye!